Why do bridges need special expansion joints? And what does it actually mean scientifically if we say two objects are the exact same temperature? So by the end of the video, you'll understand a few things. The first thing is the zeroth law of thermodynamics, which is thermal equilibrium. The second thing is how materials physically expand when heated and how you calculate that. So we're going to go through problem solving as well. First, thermal equilibrium, so the zeroth law. What is same temperature? What does that mean? If two objects are in thermal contact, so they're able to transfer heat to each other. For example, and I've used this example before, if you have a mug of hot coffee, you put a metal spoon inside. The spoon and the coffee are in thermal contact because they're able to transfer heat to one another. If you put a cold spoon in, then heat is going to be flowing into the spoon. But at some point, they're going to reach the same temperature and there's not going to be any heat exchange anymore. That point is thermal equilibrium. The zeroth law of thermodynamics is that if object A is in equilibrium with object B, and B is in equilibrium with C, then A is in thermal equilibrium with C. This law is why thermometers work. They reach equilibrium with your body, and then they stay there telling you your temperature. Let's go through a problem so we can make some sense of this, connect it to real life. The goal of this problem, we're going to understand how a thermometer eventually stops rising or falling in temperature. So, you got a cup of hot water, and you put your thermometer in there. First, the reading of the thermometer, it rises, and then it slows down, and eventually it stabilizes at 65 degrees Celsius. What's actually happening here? Initially, there's a temperature difference between the water and the thermometer, and then the heat flows into the thermometer, and as the thermometer heats up, the temperature difference between the two shrinks. And when their temperatures are equal, so the thermometer is 65 and the water is 65, the heat stops flowing. Thermal equilibrium has been reached between the thermometer and the water. And according to the zeroth law, they're now at the same temperature. Next, we're going to look at thermal expansion. So why do materials expand when they're heated? When particles vibrate faster, which comes from a higher temperature, they push outward slightly, the particles. So that means solids like metal get longer or wider. And liquids that get heated up get a bigger volume. There's an equation for this, which is also on the free cheat sheet in the description. It's the linear expansion equation, and it tells you how much something is going to expand based on the heat applied. So it's the change in length equals this, which is the coefficient of linear expansion, and that depends on the material. The original length of the object, which is L0, and the change in temperature. And for change in temperature, you would usually use Celsius or Kelvin. For example, think of crane rails, or bridges, or telephone wires. These all change in size depending on the weather. So if it's hot or if it's cold, it all changes. And engineers have to account for this in their design process. Let's go through a problem with this formula. Put it in the top so we can access it. First thermal expansion problem we're going to solve is this. A steel bridge, let's represent it like this, nice and easy. It's 220 meters long on a cold winter morning of -10 Celsius. But by afternoon, the temperature has increased to 38 degrees Celsius. And the expansion coefficient of this steel bridge, which was this symbol here, is 12 times 10 to the power of -6 degrees Celsius, -1. This is the kind of thing you're going to be seeing. Let's use the linear expansion formula to see how much our bridge expands. Let's look at the formula. What do we know about the formula? We know the original length is 220. And the change in temperature here is 48 degrees, because that's how much it went up by. So let's just go and plug everything into the formula. The change in length equals 12 times 10 to the power of -6, which is the expansion coefficient of steel, multiplied by 220, the length of the bridge originally, times 48, the change in temperature, which is roughly 12.7 centimeters. So that's how much it expands in the afternoon. This is enough to warrant the need of expansion joints in the bridge. Next problem is gasoline overflow. So we need to find how much gasoline expands and overflows from a full tank when it's heated up. The situation is a car's fuel tank holds 55 liters of gasoline, filled to the brim, when the temperature is 15 degrees Celsius. After sitting in the sun, the temperature rises to 35 degrees Celsius. And gasoline has a volume expansion coefficient of 950 times 10 to the power of -6. We're going to use a different formula, but I'll tell you a secret, it's actually the exact same formula. It's called the volume expansion formula. And what it is the exact same thing, but instead of length, it's volume, and instead of this coefficient, it's this coefficient. Same idea. So the change in volume for the gas is coefficient 950 times 10 to the power of -6 times the original volume, which is 55 liters, times the change in temperature, which from 15 to 35 is a 20 degrees increase. So times 20. This is 1.045 liters of extra volume. So if the tank is sealed, an extra roughly 1 liters of gasoline would overflow. And here's a trick concept. What about holes? Do holes also expand with heat? People often think the hole gets smaller, but in reality, the material around it expands outward, therefore making the hole larger. Go through a problem. You have a copper ring, and this copper ring has an inner diameter of 6.4 centimeters. And you have a steel rod that you're trying to plug into this ring with a diameter of 6.42 centimeters. Currently, the ring doesn't fit this rod. The rod is too wide. At room temperature 20 degrees, how much do you need to heat this ring up for this ring to be slid over the rod perfectly? The expansion coefficient of copper is 17 times 10 to the power of -6. And first, before we solve, we need to find the difference in centimeters. So why can't this fit? It's because it's 0.02 centimeters too big. And in meters, this is 0.0002 meters. That's the change in length that we're looking for. Okay, now we have the problem set up. We know what we're looking for, and all that's left is to use the formula. The formula is this, which is what we looked at earlier. And we can rearrange with our excellent math skills to find the change in temperature required, which is the unknown that we're searching for in this problem. The change in temperature is equal to change in length divided by all the other stuff. Let's plug in our value. So the change in length we found was 0.002 meters divided by the coefficient of expansion for copper, 17 times 10 to the power of -6, multiplied by the original length, which was 0.0640 meters, the original length of the thing that's expanding here. So to make this expansion happen, we need roughly 183 degrees Celsius increase in heat. Add this to the room temperatures to find the absolute value of it all. You get 203 degrees Celsius is the heat that the ring needs to get heated to in order for it to slide seamlessly over the rod. So the final insight of this video is that heat doesn't just make things feel hotter, it makes the atoms of those things vibrate, and those vibrations literally change the size of matter.